Okay, I think we are ready to go with this webinar. Welcome everybody, and you see Emily Crownover and Kurt Pinnell on the screen as well. They're my fantastic panelists today. You can see the topic here. Want to frame it really quick for you. Essentially, I started in this field in '95 after I got my PhD doing fundamental research in the laboratory and on paper, figuring out for DNAPL at the time, not PFAS. I don't think we even knew about that name yet at the time, but trying to find solutions for how to get this nasty DNAPL out of the ground. Started studying fundamental properties of TCE and PCE and came up with these curves of changes that happens when you heat from freezing temperatures to the boiling point of water, for instance, and found among other things, confirmed research others had done, that these chemicals would vaporize pretty easily if you heat to 100 degrees. So that was my beginning. And what we're doing now in the field is what you see on the picture here. And this is a full-scale remediation project in China that we completed not very long ago. And you can say, what are the steps between being in the laboratory and thinking you have a solution to doing this in a predictable way, and to actually do it where you are promising that you are doing this in situ remediation safely and effectively, so that you can, a year later, you can build more of these high rises on here and it be safe for the people living in those houses. You also have to treat them. You also have to treat all the vapors coming out, collect them in these pipes. You need to have a vapor treatment system that is treating and not emitting the odors and the vapors. You have to ensure you're not harming the surface water bodies that are nearby, etc. So we have had so many challenges to go from the laboratory into the full scale, and we've always luckily been able to address those challenges using research and development to get to where we are today. While we've been doing all that, there's also been some of the university professors that have been checking us and have been kind of keeping us honest. And one of them, and our favorite, is Kurt Pinnell from Brown University. And I'd like to start by asking you, Kurt, how it kind of came to be that you did a lot of fundamental research also with thermal remediation and kind of checking our claims.
Yeah, so welcome everybody. I started working on thermal about the same time as Gorm, maybe a little later, in the mid to late 90s. And my first project was an EPA project, and I was very curious. I'd go to these conferences like Battelle, and I'd see claims about degradation of the TC and PC and biological activity with CO2 production. And I've always been a little skeptical. Maybe it's because of my advisors when I was a PhD student. But anyway, I was like, I'm not so sure about this. And so we got a couple projects to look at that and develop these systems to look at it. So our first thing was really to look at, can we get degradation of these compounds? And we were, at that time, we were primarily focused on ERH, which is lower temperature, about 100 degrees C. And obviously those are easy to run in the lab too. Once you get above 100 C, things are tough experiments in the lab. But even then, one of the critical things is when you heat something and you're looking at gas phase, you're almost in the most difficult system to work with. And so on the right-hand side, you see, we used to use some, or a lot of studies were done in VOA vials, and we found that those don't work at all. And you can't get mass balance. You have all kinds of losses. And so we went to these sealed ampules you see on the right. And the cool thing about these was you can have 3 phases. So you can have a solid phase, a liquid phase, and a gas phase. And then when you crack these open, after you say heat them for a couple of weeks, you basically crack them open, but you invert them. And if you hold them at an angle, the capillary pressure holds the water, and you can actually stick a needle through the water into the gas phase and then collect your gas phase sample and inject it on the GC. And that's what we did to look for these daughter products. And what I wanted to show for this slide was we looked at a lot of different sites. And we didn't see a whole lot of degradation of TCE and PCE at these temperatures. And I won't go into all the details of those studies. You can look those up if you want. But the neat thing is we started to see at higher temperature, we did see a lot of CO2 production, which people had seen and attributed to biological activity. But it was really the soil degrading. So you were breaking up some of the soil organic matter. And on the right-hand side, you'll see we started creating things like acetylene. When we had one time we had an explosion in the lab because we created too much acetylene. And then we have other compounds that actually can break down and serve as electron donors for biological activity. And that's one of the things that we've seen and we studied in a subsequent study. So the key thing here is if you see reaction products, it doesn't mean that the parent compound is really breaking down. It could be soil degradation. And also it's really hard to close the mass balance unless you have a sealed system. So if you're in the field and maybe Gorm or Emily are trying to, figure out where the mass is, it's really hard when you heat things up and put them in the gas phase. And so we had to go to these ampules in order to get that done in the lab.
You also looked at biological reactions with Frank Loeffler when you were at Georgia Tech, didn't you? And studied basically the temperature on bio. Yeah.
Yeah. So at that time, there was as many of you know in the remediation world, dehalocortias was discovered and it could break down cis-DCE to ethene. And so there's a big push to do bioremediation. And what we were trying to do was combine thermal and bio. That was the base of the project. And this is a really complicated slide, but it's just try to illustrate what we're looking at. So on the left-hand side is we ran a column study at low temperature and we're feeding it PCE. And so we were able to get the PCE, of course, to degrade very quickly as soon as we started the experiment. And these were columns that were inoculated, so they were good to go. We'd get cis-DCE and we didn't get a lot of transformation to ethene. But you'll see at about 50 pore volumes, we switched over to 35 degrees C and the activity increased dramatically. So within the given residence time, we were able to we saw vinyl chloride. And then at the end of the experiment, you can see we're basically producing almost complete ethene from PCE. And so we found that at these temperatures, we could really accelerate the rate of PCE transformation to ethene by microbial reductive dechlorination. So it was a really cool study, and we were able to show that this actually could accelerate the degradation process.
Mm-hmm. And so in the industry, you hear a lot about reaction rates doubling for every 10 degrees. You heat something up. Would that be true for this reductive dechlorination as well?
Yeah. So the interesting thing about this, Gorm, is it works really well up to about 35 or 40 degrees C. And we get that type of increase, really dramatic increase. But above those temperatures, dehalocortias turns out to be quite sensitive to temperature. So what we found was when you get above about 40 degrees C, the dehalocortias shut down. They can rebound back, but they won't really function actively at those higher temperatures. So from a practitioner perspective, you may see this type of accelerated degradation occurring outside the actual really hot zone of your treatment system.
Yeah, fantastic. So Emily, you lead the research and development project or program for a pretty small company with 70 people. I think it's relatively unusual that a company that size has its own research and development program. And would you mind explaining to us how that is and why we have that?
Sure. Yeah, the short answer is that it helps us bring technology improvements to the field faster. So I completed my PhD in 2010, and what really drew me to TRS was having the opportunity to actively integrate research into field implementations. And TRS, we've been developing our R&D program over the last 20 years, and we have employees across the company that support our R&D program. Over half of our employees are actively contributing to R&D projects. And essentially, we have three different branches to our R&D program. We have a lab branch, and essentially within that branch, that's where we perform treatability tests. We evaluate new emerging contaminants and the different target temperatures that we would need to reach remedial goals. We also have a field implementation branch. So that's where we really focus on heating optimization and improvements that we can make to our designs and our heating infrastructure, our equipment. And then our third branch is post-heating analysis. So we put a lot of time into analyzing all of the data we collect during thermal remediations. We collect and maintain all of that in a database. And essentially what we do is we look at all of the data that we collect and we compare those data sets to what we would have predicted in our thermal modeling. And this has helped us over the years to actively refine our thermal models and improve our ability to estimate the amount of time it takes to reach remedial goals.
You mentioned laboratory. What have you done for PFAS in research and development?
Yeah, so multiple years ago, we did an evaluation in the lab looking at different temperatures and the PFAS reduction percentages that were achieved. A snapshot of that research is shown on the left-hand side. And what we were able to see is that we could achieve a 99.998% reduction of detected PFAS at 400 degrees Celsius. And then as a follow-on to this work, we also worked on heating infrastructure optimization to reach these target temperatures, and also the vapor and liquid treatment equipment that would be required. So when we're volatilizing and removing these PFAS impacted vapor and liquid streams, we want to make sure we have the equipment that can handle and effectively treat these compounds.
Yeah, what are we looking at? What are we looking at over here on the right side of the slide?
Yeah, so here is a snapshot of just some of our testing facilities. So we do lab testing, but we also test our heating infrastructure as well. So for our heating technologies, we're actively trying to improve them all the time. So that middle picture is showing one of our heaters. It's part of our heating infrastructure for TCH. And then on the right-hand side, those are two pictures from our test facility. So when we are making improvements to our heating infrastructure, we test them at our test facility first before we bring them to the field. And that's been a big part of the last several years. It's helped us really expedite our ability to bring new technologies and improvements into the field.
Very good. So, but I guess it's not enough to have the heaters and a way to put them in the ground, right? You also have to make sure the soil in between the heaters gets really hot. How are we studying that?
Yeah, so we put a lot of focus in our research in power optimization and power delivery. So on the left-hand side, that shows a picture of our power control units. That's one of the pieces of equipment we use to monitor and collect all of our power data. And we use this data to evaluate an energy balance of our system. Essentially, actively during a thermal remediation, we want to look at how effectively are we heating a treatment volume, and how does that compare the required energy that we would have anticipated needing to what we actually input. And then what that can give us when we're actively evaluating that can help us help show us if there's unexpected cooling effects that might be occurring. We can actively adjust and modify our heating infrastructure in the field. So in terms of thermal conduction heating, one of the improvements we can make in the field, on the picture on the right-hand side, that is an example of a heater build. And if we see that we're not heating as effectively at certain depth intervals as we would like to, we can modify those heaters in the field. So we can essentially modify it. We take measurements to ensure that everything is within design parameters, and it doesn't require any welding, and we're able to replace that heater within about an hour once the heater is built. And so it's essentially a big part of what we focus on, and because we know if we can optimize power delivery, the more effectively we're able to deliver power, the faster we are able to heat up and reach the overall remedial goals.
Very good. Kurt, I know you're involved in PFAS research as well. And would you mind explaining to us kind of how you choose your topics and your research focus, and how you came to be involved in PFAS research?
Yeah, sure. Gorm, I had one quick question. Do you want me to try to answer the question from the audience, or let it go?
Go.
Okay, there's one from Brent. Odell, and he asks, from a practical perspective, how long can temperatures be managed to enhance biodegradation of chlorinated amines? Has any work been done looking at this? So my perspective, and of course, Gorm and Emily might have a different view of it, but my thought on this is that when we have this heating, low temperature heating, it could occur outside the really strongly heated zone and after the heaters are turned off. And so then you can get this sort of beneficial effect that you may view as a polishing step. And then the other way to approach it is if you wanted to actively do this, you could do some other type of low temperature heating, perhaps with hot water heating. But from my perspective, it wouldn't be practical to put in a big thermal remediation unit to heat to 35 degrees C. And Gorm may have thoughts on that too, but that's how I view it. I would go a low temperature heating thing that might just be hot water. But the heat will stay in the ground pretty long. Gorm, what's your estimate on that?
Yeah, completely dependent on the shape of the treatment zone and on especially the groundwater flow. We've had sites that have remained very warm for 2-3 years, and those are the big deep ones that are relatively tight, right? They cool off very, very slowly. And then we have sites that are smaller or narrower, or where the water moves fast, and they return to ambient in 6 months or so. So it's very variable. The model that Emily shows here, the energy balance model, can also be used to predict that cooling. That's one of the things we can get out of this model as well. And we do sensitivity studies sometimes for that, just depending on, do we need to cool it down quickly or do we not? Most of the time we don't need to actively cool it, and we just let it slowly dissipate. Right. Yeah, I know you're trying to avoid my next question, which was how did you get into PFAS research? But if you don't,
no. So as an academic, a lot of you may be practitioners, but some of you are probably academics out there. But my view of the world is I have a skill set, and I sort of we have to change with the time. I started working on jet fuel, pesticides, and then JP4 jet fuel, then chlorinated solvents, and now I work on PFAS. And in a way, I have to shift with where the interest is and the funding. Not entirely different from what a consulting firm may have to do to stay current and active and publish and get research money. So we have to get research dollars to support our program. And this picture shows a bunch of grad students and postdocs that are in my group, and that we work hard, but we still have fun. Part of the reason I like academics is it keeps me young, because I work with a lot of younger people, and I try to help their careers and send them off to work for people like Gorm and others in the industry. And you can see on the right, I just showed some of the collaborations. We now have funding from CERTIP and EPA to look at PFAS remediation and fate and transport. And so my expertise is really in fate, transport, and remediation. And I collaborate with a lot of industry partners, and TRS is one of those. And you'll see Jacobs and Woodard and Carr and Geosynthec there also. And I really like having those collaborations with industry, because in a way it drives my research to make it more practical. I mean, we still do very fundamental work, but how can we relate that or help advance the field so that practitioners can do a better job with their cleanup and answer questions? And PFAS is a really hard one. I think one of the key things, or one of the limitations for me, was the equipment. So I do a lot of chemistry, as Gorm knows, and Emily. And so one of the barriers was having the equipment to do this analysis. And this slide shows one of my students here on a GC orbit trap, and on the right hand side is an LC orbit trap, and on the left hand side is a LC triple quad mass spec. And so we have these three instruments in our lab. These are not inexpensive instruments, so it's kind of crazy when you think about how much money these cost and the service contracts. But we do a lot of our targeted analysis using the instrument on the left, the waters. And then the GC we do for more volatile compounds. So we can look at also volatile. We can do targeted analysis and non-targeted analysis. And on the right-hand side, we use the high resolution orbit trap to do mostly non-targeted analysis. And what we mean by targeted is, like, a lot of times now EPA or CERTIP will say, you've got to measure these 28 chemicals, and we have known standards for all those. We have labeled standards. And one of the real challenges with PFAS is that there's not standards for everything, and there's certainly not labeled standards that we can track for all the compounds. So that's where the non-targeted comes into play, which means you basically measure everything in your sample, and you can pick out fluorinated compounds because of the mass resolution defect. And then there's some databases where you can then match those using MS2, so that basically triple quad analysis. The problem is quantification. So we get what we call semi-quantification. So you use a reference standard that you think is close in terms of its ionization energy and those types of things. And so you can get a semi-quantitative or a qualitative assessment of how much is there, even if you don't have the standard. But you have to pick a compound that's similar to it and see how it responds to mass spec in that matrix. And then you can use that to get an idea of if it's high or low and a rough concentration.
Yeah.
But that's the kind of crazy stuff we do in the lab now. And I would say this is one of the biggest barriers to doing research. And especially if you want to do low concentrations. So, you know, and when we get into this, everyone is like, well, did you get to the target concentration, either it's a soil concentration or water concentration? You can study reactions at 1 milligram per liter. A lot of people do that, and it's relatively easy to measure it. You don't need quite a sophisticated instrumentation. But when you're trying to measure 20 parts per trillion of all these different compounds, it's definitely a challenge. And this is probably the biggest barrier for people to get involved in this research.
Yeah. And of course, you've seen other people in the industry treating PFAS with different temperatures, but you had to make your own experiments as well, right?
Yeah, of course.
You did, and which is fantastic.
Yes. So you saw Emily show some data before, and not that I'm entirely a skeptic, but I like to, make sure it's good. And one of the reasons Gorm and Emily are great to work with is because they don't mind me trying to reproduce their data and trying to figure out what's going on. So we took on this ESTCP project, we're trying to do a heating at Eielson Air Force Base in Alaska. And so we've got the soil from that site. And what you see here is we just show 6 of the target PFAS we looked at here, but we basically heated this soil up, and it was a temperature ramp. So just let me explain this for a second. We started at 0, of course, time 0, and that's on the left. And then we heated for 1 hour at 100 degrees. And then we heated for another hour at 200 degrees, another hour at 300, and then another hour at 400 degrees C. So it was a temperature ramp. And what we did was we destructively sampled at each point, and that's what each of those numbers represent. So on the right-hand side, that was treated up to 400 degrees C. The total treatment time was 4 hours, but it was treated 1 hour at 100, 1 hour at 200, et cetera. But what you can see is we basically got the same information that Emily got, which is you need to get to, above 300 heat and till you see this removal. And then we see complete removal of the target compounds below the concentrations that we can measure or below the target concentrations. So the nice thing is we were able to reproduce what Gorm and Emily had seen in their preliminary studies, which is always a good thing.
Yeah, and it was astonishing that this was accomplished in 4 hours, where in our laboratory studies, I think we took 2 weeks or 10 days and in the field we spent at least that long at temperature. So this is pretty amazing. But I guess we don't believe that this is complete removal so quickly, do we? Or at least I know you also looked at other compounds, not just these targeted compounds.
Right. So that was it. So the next thing is, of course, I'm always looking for, we're trying to get mass balance, and it's really hard in these systems. And so we're trapping the off gas. And again, these were laboratory scale studies that were done in a column that was inside a quartz crystal column. And we put the soil in there, and then we heat it up in an oven, and we blow nitrogen through that. And then we collect the off gas, and we try a number of different traps, but we're mostly settling on liquid traps now. And then we analyze those. So what I want to show you here, this is the soil, not the traps. Before we have data for the traps, but this is just an example. If you just look at the upper figure, you'll see the compounds that we're interested in red. Those are the 6 that we're monitoring. And this was done on the LC Orbitrap mass spec. And those other data I showed you were done on the waters. But what we found was we did targeted and non-targeted, and we can see a lot of other compounds in the soil, right? Which is, I think that's just the way it's going to be in reality when you have a site that's contaminated with AFFF, for example. You're not going to just see the compounds that maybe you see in the news or people are, have on a list. And then down below, we see after heating. And what we see is that the targeted compounds, as we saw with the waters analysis, all those were removed. We can't detect them anymore. But we're seeing all these different products, different fluorinated. Some are short chain fluorinated. You'll see a lot of it shifts to the left. We see a lot more short chain. So as you go to the left, these are lower molecular weight. So you can see the molecular weights where the lowest is 60. The other thing you notice is the area counts are lower. So these are on different scales, but you'll see some of these compounds and a shift in these different compounds. So these are what you might call these are the condensed byproducts. So these were in the still in the solid phase, all right. And we also have data for the gas phase, the samples we collected. But we see these products. Some of these were there before, and they're still there after. Okay, and we're trying to. So what we're really doing now is trying to understand this. This is where the research part comes in. We're trying to get mass balance and identify these and quantify them, and understand which ones were there before, which ones were created. But as you can imagine, it's a very complicated scenario because we have so many chemicals and we have these reactions happening on top of that. So that's where we're at. This is what we're trying to, this is research basically. And we're trying to help basically advance the field by understanding this and making sure we can get rid of these compounds. And one thing that's really important to remember here is, Gorm mentioned this before, we only heated this for 4 hours at 400. So this isn't as long as you might heat. And we're going to extend this and see what effect that has. But we had to start somewhere. So we started at a 4-hour heating of this. And this was a real field soil. So obviously it's a lot easier if you spike a soil with, PFOA and then look at what happens. And we're doing those types of experiments too. But this was a real field soil. So it's probably the worst case scenario in terms of the analytical chemistry.
Mm-hmm. There is a question that came in. A question came in basically saying, what are the PFAS byproducts in the gas phase? And I know we don't have the answer to that, but maybe I ask Emily in the next question, and then we can kind of talk about that one after that, because we are studying that at the field scale, right? So Emily, with all that we've done so far and what we've learned in the laboratory, how close would you say we are to having a solution for PFAS in soil?
We are very close. So we are still working, as Kurt mentioned, on optimizing the heating duration that would be required to reach the targeted PFAS concentrations. But through a lot of the work that Kurt is doing, we recently received ESTCP funding. So Brown University and TRS are both subcontractors to an ESTCP funded project. And we just finished installing all of the heating casing infrastructure this week. There is a pile at Eielson Air Force Base where we're able to heat the entire pile in the field demonstration, and we will be actively heating this in the next couple of months. So we're very close. And as part of the ESTCP project, they are investing a significant amount in analytical. So we are able to have OTM 45, which is a rigorous vapor analytical technique and method that we're using. And we're looking at our different vapor and liquid process streams and being able to analyze them at a level that gives us a lot of certainty of to ensure that we are extracting PFAS, that we're heating, and any byproducts that could potentially be formed.
Yeah, so just to follow up on that, we'll basically at the field site, OTM 45 is a collection process that EPA just put out. And some of those samples will go to a commercial lab to analyze for PFAS. And then some of them will come to my lab to look at the byproducts using the non-targeted And so that's how we're going to look at this in the field to see what products are forming or we're collecting in the gas phase. And then also look at how we can treat that gas phase stream. There was one question from Brent about, did I read correctly, some of the area counts went up? And the answer is yes, some of the area counts would go up because we're forming, byproducts. And so some things will go up and some things will go down. And this is pretty standard. Even if you do, oxidation of PFOA, you'll see a lot of studies in literature. The PFOA might go away, but they're creating a lot of other compounds. And so if you do the analysis to look at everything, you're creating compounds. You're not necessarily breaking it down just to HF. And so that's part of the challenge, I think, with PFAS remediation is that even if you do plasma, you'll see a lot of byproducts being formed. So you have to be careful and do this type of analysis that we're doing. And it's expensive and it's sort of, but I think it's necessary because we have to be careful about the things we're producing.
And we're selecting a safe option for vapor and liquid treatment here. So rather than trying to target oxidation, Kurt was mentioning byproduct formation, we're using carbon for adsorption. The majority of PFAS that are removed from the stockpile will be transferred to the aqueous phase, but there's a small amount that will maintain in the vapor phase, and we're using carbon for adsorption just to help remove, the potential as that's still being better understood. And there's a significant amount of ESTCP resources that are being invested in higher temperature, trying to destroy these compounds at higher temperatures. So as we continue to understand that better, we wanted to go ahead and go with a safer option with carbon treatment for vapors.
Yeah. I may want to just mention one thing on this slide. There's a little bit of an optical illusion that these peaks look bigger than these because there's different scales here. So that's a technicality, but it's absolutely correct. There are things that get created and increase in concentration. Emily, so on the screen we're seeing the one pile at Eielson Air Force Base, right? I know they have like 52 piles for full-scale treatment. Are those some of the ones we see in the background?
They have over 100,000 cubic yards of PFAS impacted stockpiles. So as part of this demonstration, we're looking at the effectiveness of PFAS thermal treatment, and there's a potential for cleanup of all of the piles. And Eielson Air Force Base is very motivated to be able to treat these piles.
Okay, very good. What other research projects are we doing for PFAS?
Yeah, the Department of Defense has been very interested in PFAS research recently, and we are a part of TRS 4 different Department of Defense funded projects. So 2 of them are focused on PFAS thermal treatment. So one is in collaboration with Kurt Pinnell and Brown University. And then on the other, we're doing it, that's for an ex situ demonstration. And we're also doing an in situ thermal treatment. And that's in collaboration with NAVFAC and Jacobs and Patel. So a lot of support there. And then we have 2 other Department of Defense projects that are focused more on PFAS water treatment. And we're using a perfluoride flocculant technology, and then also clean out of firefighting systems using this perfluoride flocculant technology.
Fantastic. Kurt, maybe a little bit unfair question to you, but with everything you know now, do you think thermal treatment will end up being an effective solution for PFAS treatment?
Yeah, so I think in a lot of situations, I think it'll be a cost-effective and an effective technology for treating PFAS, especially if we can figure out all these byproducts and things like that. I think that's the key. And I think actually that's the key for all technologies going after PFAS. And it's, we just have to be looking at it, and we're sharing our data. And we got to, one question was like, how do we ensure this? And the way we ensure it is to look for those things. If you don't look for them, you won't find them. And if I just showed you the one figure with, the 6 PFAS going down that are the ones on the regulated list, everyone would be happy, right? We'd say, oh, we're done. But that's, we try to find the mass balance, and that's what we do in the lab, and that's what we're interested in. So we're trying to figure out where that mass is going. And that's why what we're trying to do to ensure that it'll be effective. I'm certain that we can, with thermal, you can remove those targeted compounds. The question we have now is how do we do the mass balance, and how do we make sure that we removed a lot of these byproducts? And if we leave some behind, are they below levels that are acceptable from a risk perspective? And that's a bigger question, but I think that's where we'll be headed. But it's true I want to emphasize, it's true for a lot of technologies. These things are not easy to break down, and you may break down the parent, but you need to look for the daughter products in order to say that something is, effective in a way. It's going to be, I'm pretty sure a lot of technologies are going to be effective to remove the parent, but to remove everything is going to be the challenge, in my opinion.
Thank you very much. I have one more, and then we go to open Q&A, and all of you people out there, I've seen you do it in the Q&A box, but also in the chat. It doesn't matter where you do it. We will read them and try to answer them before we are finished. We have about 10 more minutes left. So one more question. Basically, Emily, the sort of ESTCP program, what importance has that had for our research, and how do we look at that now?
It has been such a great experience for TRS to be a part of that community. The amount of idea sharing and collaboration, we feel very supported just through all of these projects. We have regular meetings, where investigators get together and we're able to share ideas and help share our lessons learned and things we're learning as we're doing testing, both in the lab and in the field. And it's such a nice opportunity to be a part of an environment that's full of firms that are implementing in the field, but also universities that are actively evaluating and looking at more closely at what's actually happening in the field. And I think that's one of the things we have loved so much about working with Kurt is our eyes have been really opened as well on further, what exactly is happening in the soil through this non-targeted analysis. And it's at the end of the day, we want to get the soil clean, and this analysis is helping us to do that. So we're just excited to be a part of it, and it's been just a really good opportunity for us as a company.
Yeah, and for me, I really like the ESTCP program because I get access to field materials and get to see what's actually going out in the real world, and not just stuck in my laboratory. I'm not sure I'm going to make it to Alaska, but I make it to some sites, and it's just good to get out and see that the work we're doing is helping to support advancement of the basically the profession of environmental engineering and remediation. So that's really the goal of my research, is to help advance the field as best I can.
Kurt, I think we need to schedule a field trip to Alaska.
Yeah. So there is a few questions I'm going to start reading now. One of them is impact of PFAS reduction at higher temperatures, such as 800 degrees C. It's not really directly a question, but I guess it's someone wanting to know at much higher temperatures if things would be very different.
Yeah, I can try to answer that. I don't know the answer for sure, but my view is yes, it'll be different. And higher temperatures are in some ways easier because you might get complete conversion. We have a study that's just starting with sort of to look at reactivation or treatment of activated carbon that's been used. So spent activated carbon that has PFAS on it, and what happens when you heat it up to 1,000 and collecting the off gases and looking at those reactions. And we're working on another project with EPA and one of their incinerators to look at that too. I'm mostly doing the analytical part of it, and then other people are doing the theoretical chemistry for that to predict those reactions, starting from the smallest molecule and building it up to and also going to condensed phases. So there's a lot of work out there. I don't think we know the answer yet, but basically you're going to get most likely more reactivity and different products, and also potentially more shorter chain products forming. And that's what we've seen so far, but we're just starting that project. Yeah.
Kevin Mumford has a very good question about fluorine mass balance. he says, as you work towards improving mass balance, what's a reasonable expectation for fluorine mass balance given the current analytical limitations or capabilities?
Yes, this is a great question. So I think some of the higher temperature studies, it's been easier to do the fluoride mass balance. The lower temperature studies where we potentially have partial reactivity, it's more of a challenge. So we are shifting to do total organofluorine analysis on our samples, like they call it ETOF or TOF analysis, to complement the non-targeted. So to get to your question, what's a reasonable mass balance? If I can get to 80%, I'll probably be pretty happy. If 50% is probably the lowest I want. But the other thing to remember is that we're dealing with gas phase. So, unless you can have a sealed ampule like that nice system I had when we started off with TC and PC, it's going to be tough. But that's what we'll try to do as best we can. But I think reasonably, if you can get 80% mass balance, you're doing pretty well if it's just on a fluorine basis. So it's important to remember everything in the gas phase is a little more tricky to deal with than in the liquid phase or in the aqueous phase.
And there's another good question from Stu Abrams. Are there any commercial in situ projects for PFAS remediation? And I can maybe, to my knowledge, no, but that doesn't mean it isn't occurring, but we don't know of any, in situ PFAS. We have one of the demonstration projects Emily has up on the screen here is that the top one. That is also in the ESTCP program and on the way into the field, but I haven't heard of any in situ treatment being done commercially. I know that that Jacobs did another demonstration for ESTCP with an infrared reactor, kind of above grade, so it wasn't an in situ demonstration. We know our Danish colleagues from Kruger has done laboratory experiments and had a webinar about this a week ago, but as far as I know, not in the field at this point. So with that, I think Kurt and Emily, feel free to pick a question if you see one that you'd like to answer. We've been around most of them.
There's one interesting one here, Gorm, if you don't mind.
Take it.
It's from Joe. I'll probably destroy his last name, so I won't try it. But it says the research is way ahead of regulation. Shouldn't regulation drive the research focus? I mean, to me, that's a really good question. And my answer is, I don't think so. I'd rather, the way the regulations are moving now, they're so slow. When we're in that site in Alaska, they regulate the soil for only 2 compounds. So technically we could treat to those 2 compounds and be good to go. But my view is, if we want to really advance this science, advance the field, and apply thermal in a broader place, we need to understand these other things that are happening. So in my view, I'd rather be ahead of the regulation. And also the way it takes so long to get regulations put in place, I prefer to be ahead of it. I don't know what you think, Gorm and Emily, but that's just my view of it.
Absolutely, yes. That we are very enthusiastic to be working on and spending a lot of our resources on coming up with basically, you could say it's a vaccine we're trying to develop for this illness, right? Even though it isn't quite, all of it isn't quite understood, but we need to be working on these methods that are better and stronger than the challenge right in front of us, so that when the regulations change, we're ready for it. Especially when it comes to this PFAS and AFFF sites where there's firefighting foams and things, and regulations are already being talked about of, having to remove these chemicals in 2 to 3 years. And if we are not ready with a technology now or a year from now, that is just not going to be practical. The other thing is that we can help the people within the regulatory agencies. We can help them also determine what can be done, because it doesn't make any sense if they say, you need to treat to 0.0007 ppt, and then it's not technically practical. We can, by being out in front and doing these demonstrations, we can also show them what is technically feasible within a reasonable amount of money, essentially, So if they regulate something that costs $10,000 per cubic yard, it probably will not be performed. But if they regulate to another standard that is still safe and can be done for a reasonable amount of money, then it's going to happen. So it all kind of ties together, and I think we need to all contribute where we can, and not just wait for somebody to tell us this is what you need to do. Bruce Thompson had, as always, a really good question. he always has them. What is the expectation for timing of a pilot for an AFFF site where you treat for PFAS as well as the typical fuels and solvents associated with fire training? So I think he means to ask, if we're doing a pilot test at an area like that, how long would it take? And if we were just treating PFAS, would it be about the same as if we're treating PFAS, along with solvents and oils that were in the same area?
Yeah, I can take that, Gorm, if you'd like.
Yeah.
Yeah, so essentially it depends on the treatment volume, dimensions, and geometry in terms of the amount of time it would take to heat up the soil volume to the target temperatures. But if there are co-contaminants, in general, they would have boiling points that would be lower than our target temperature for PFAS removal. So we wouldn't expect that to significantly impact the duration of heating, because we need to achieve the boiling point of water first. We boil off all the moisture, and then we continue to heat up to 400 degrees Celsius. So any co-contaminants that have boiling points below that temperature range, we would expect to volatilize. If there is LNAPL present, then that would change how we would design our vapor and liquid treatment equipment. But it would just be something we'd want to be aware of so we could account for it in our design, but it shouldn't significantly impact the heating duration.
Fantastic. I think we will wrap up the webinar now.